So first of all, what we're going to do is highlight a couple of definitions and then really talk about what does it mean to be in standard position. We've got a terminal arm, a terminal point. So you've got some definitions to talk about here and really understanding what an angle is in standard position. For the most part, trigonometry in grade 10 dealt with triangles. Makes sense? But triangles, if you draw them, it is possible to sometimes have an angle bigger than 90 degrees, right? So we're going to have to figure out how do we do math with triangles that aren't just 90-degree triangles. Because grade 10 math, SOHCAHTOA, a squared plus b squared equals c squared, only works if one of those angles is 90 degrees. And you have a right angle triangle. So, we're going to deal with angles that are bigger than 90 degrees, which you know that they do exist. So mathematicians say, well, if someone is talking about an angle of 120 degrees, they like to get some sort of standard so everybody knows we're talking about the same thing. So what we have is we have your axes, right? Your x and your y axes. And if I was talking about 120 degrees, 120 degrees would be drawn like this. I don't know how accurate that is. That would be 120 degrees. I would never draw 120 degrees. If someone said 120 degrees, I would never draw it like this. Even though that angle is 120 degrees, this is 120 degrees in standard position, the blue. This is 120 degrees, not in standard position. So we want to have a basis for talking about something when it's in standard position. Okay? So what I'm going to do is I'm going to play a little game. I'm going to give you an angle, and you have to tell me if you think it's in standard position, yes or no. Here's the first one. How about that one? You think that one's in standard position? Yeah? Okay, good. All right. Oh, man. I was going to move it over here. There we go. How about that one? No. No? Okay. Yeah, I don't like it. How about that one? Yeah. Yeah, okay. That one is a yes.
It has to start at the top right.
What about this one? No. No? All right, you got that one wrong.
What?
Okay. What about yeah. Okay. I'm going to apologize to you right now because you didn't notice this, but I just hypnotized you. Right now, with those spirals, you guys are currently in a hypnotic state. I can influence. This is really dangerous because I have all sorts of power right now. Don't worry. I'll just, when I snap my fingers, you'll come out of it. But some good things that'll come. You like math, right? When you get home, you'll be like, I feel like I should do math homework, right? And you won't know why you have these feelings. They'll just sort of like this is weird. I've never experienced this before, but okay. So, right. There we go. You're not going to remember any of that. You can watch the video later to find out what happened, but yes or no?
Yeah.
Yes. Okay. So what makes something in standard position? What's the rule for standard position?
If it like comes out of the top, like right one.
It has to start here, right? I should have done one more like this maybe, where I had that. That's another no, because the arrow's in the wrong direction. It has to start on the positive x-axis. And actually, we talk about angles going counterclockwise are positive angles, like this 120. The first one that you got wrong, which was this one here, this could be like minus 60 degrees. That would still be in standard position. So, after drawing all of that, maybe we just write a little statement. An angle in standard position has to start on the positive x-axis, not the negative x-axis. Okay, next thing that we're going to add as extra notes are the following special triangles. Okay? And with his special triangles, there's actually, let's see here. Yeah. There are some things in trigonometry now in grade 11 and again in next year in grade 12 pre-calculus that you have to do without your calculator. Okay? Before, like if I told you sine of 30 degrees, you'd have to go to your calculator. Some of these we're going to be able to do without our calculator. Okay? And we can do them without our calculator if we have special triangles that we know how to work with. Okay? The first angle you're going to be able to, the first thing you're going to be able to do without your calculator is tan of 45 degrees. Does anybody know it already? Good. Check it on your calculator. You do tan of 45 degrees. Do you get 1? Why? Okay. The answer to why it works is with a special triangle. So SOHCAHTOA deals with right angle triangles, right? So if I want to do tan of 45 degrees without my calculator, I draw a right angle triangle and I make one of the angles 45 degrees. And this is special. There's stuff you can tell me that I haven't written down yet. What can you tell me about this triangle? Yes.
It's 90 degrees.
This is 90 degrees, yeah.
So the other angle is 45.
The other angle also is 45. Okay. What else can you tell me about this triangle as a result of that? This is a right triangle, but it's also there's another special name for this triangle now. It's isosceles. Isosceles is when two angles are the same and what else? Two angles are the same and
two side lengths are the same?
Two side lengths are the same. So now I know that if this is 45 degrees and this is 45 degrees and it makes an isosceles triangle, that this length here and this length here are the same. Now the power of trigonometry that you learned in grade 10, is that the ratios don't matter how big or how small that triangle is. Tan of 45 degrees is supposed to be 1 no matter what. No matter how big or how small. How big do you want to make this one? How long is this side? Make it any number you want.
67.
67. Do you know any other sides? Don't write the 67, because that's going to make our math harder. We're going to do a squared plus b squared equals c squared later. That's going to be like... But, if you know this side is 67, then this side has to be 67. And tan of 45, tan is what over what? SOHCAHTOA? Opposite would be 67 over 67. Do you get 1? So we could get that 1 without a calculator just by drawing a triangle and seeing what we notice. Now, for our mathematics, you could now figure out the hypotenuse. But you have to do a squared plus b squared equals c squared. 67 is not a good number to choose if you wanted to do this without a calculator. What might be a nice number to choose if you wanted to do this without a calculator? 2. 2 wouldn't be bad. Any ones that would be even easier? 1. So if I use 1, and 2 would be exactly the same, not too hard. Can you do a squared plus b squared equals c squared? You would have 1 squared plus 1 squared equals c squared. 2 equals c squared. You agree that, now normally when you square root both sides, you're supposed to do plus or minus. Why didn't I do plus or minus this time?
What was too special?
Because what am I talking about? I'm talking about a length. Can the hypotenuse be a negative length? No, doesn't make sense. So mathematically you should do plus or minus. Situationally here, only the plus makes sense. Maybe I should show that work that I thought about it and did it correctly in the end. Okay? You know what that lets us do? That lets us do sine of 45 degrees without our calculator. What would sine of 45 degrees equal? SOHCAHTOA. Pick a 45. Doesn't matter which one. What's the opposite side? 1. Over the square root of 2. Are we allowed to have square roots on the bottom from our square roots unit? No, so we have to rationalize the denominator. So we're going to have to multiply top and bottom by root 2 to simplify this to be root 2 over 2. So now you could do tan of 45 without a calculator. Sine of 45, can we do cos of 45 without a calculator then too? Cos of 45 degrees would be adjacent, which is 1, over root 2. Oh, that's exactly the same. Can you see that's the same? It's going to be root 2 over 2 as well. So I'm going to ask these on your quizzes and tests on the non-calculator part. What is cos of 45 degrees? And you'll have to come up with root 2 over 2. So you can choose. Some people just memorize it. And some people like, oh, if I can redraw the triangle, I can figure everything out. Yes.
If the side lengths are different, would it still be root 2 over 2?
That's a good question. So let's choose. I love that question. Because someone said 2 wouldn't be hard to use, right? So let's say you chose 2. And you did a squared plus b squared equals c squared. 4 plus 4, this would be 8 equals c squared. Which c would be plus or minus the square root of 8. But since it's... Okay? And then I do cos of 45 degrees with this one. Can you see that you would get 2 over the square root of 8? Can't have square roots on the bottom. Also, we should always have our square roots in lowest terms. So, can I reduce square root of 8 to anything? 2 square root of 2. If I do that, can you see your square 2's would simplify? And you would be left with, uh-oh, same thing. And then if you rationalize, If you did 3's, you would get square root of 18 here, which is 3 square roots of 2. And the 3's would cancel out and give you 1 over square root of 2. And if you did 67, you would find out that the hypotenuse is 67 square roots of 2. And then you could cancel out the 67s and get 1 over square root of 2 again, which is the power of trigonometry. No matter how big or how small your triangles are, the ratios always stay the same. This is special triangle number 1. You have to be able to do 45 degrees without a calculator. Special triangle number 2. The other angles you can do without a calculator are 30 degrees and 60 degrees. So we start by saying, okay, well, I'll draw a triangle with 30 degrees. And if I did that, you would know that the other side would be 60 degrees. And this one's trickier than the 45 degree one. Because the 45 degree, if you recognize that it's isosceles, you're done right away. Okay? As far as triangles go, they gave names for special triangles. Like there's a right angle triangle, special because it's 90 degrees. Isosceles, 2 sides, 2 angles the same. Equilateral, all of the sides the same. But then they were like, oh my goodness, there's a whole bunch of triangles that, sorry, they're really not special. They have all different angles and all different sides. And you probably, I don't know, does anyone remember the name of the everything else of triangles? Starts with an S. Second letter is a C. Scalene. They even sound scaly like it's that, I don't know. It's like they gave it even a name. I don't know, it's just not. So this poor triangle, really, all the sides are different. We're really stuck because we're trying to do this without a calculator and there's nothing we can do. So I'm feeling kind of bad about this triangle. This triangle's probably feeling bad about itself. So it's you know, as triangles do, it's walking down the street, it's all sad, not feeling very good, and it runs into somebody else that's also scaling, also 30 and 60, and like, hi, they're both sad, like, I'm not special either. They're sort of going back and forth with this, and then they're like, well, do you want to be friends? And they're like, yeah, let's be friends. So the other triangle said, let's be friends, and they started to hold hands like this. It's really a beautiful moment. And they got together, and something special happened. Do you see what special thing happened when they got together? What did it make? Do you see it?
Are all the sides the same way?
Now all the sides are the same because of the 60, 60, 60 is the big triangle's equilateral. Oh my. So if all the sides are the same, you could pick any number you wanted. There's a number that works the nicest, but you could pick any number. We could do 67 again. No, we're not going to recommend it. The number that's really nice to use is you say, well, let's say this side is 2. Does that make sense? And then over here, this would also be 2. And if the whole bottom is 2, that makes this 1 and that 1. And if you have 2 sides, can you see that we could figure out that 1 squared plus b squared, because we know the hypotenuse is 2 squared, then b squared would be 3, and b would be plus or minus the root of 3, which would only make sense if it's positive. And if you put two 30, 60, 90 triangles together, then you can do a whole bunch of math without your calculator. Let's start with the 30 degrees ones. Let's start with the nicest one. Try it on your calculator. What is sine of 30 degrees?
So,
0.5. Can you see it on the triangle? Sine is opposite side. What's opposite to 30? The 1. Divide by hypotenuse. What's the hypotenuse on the blue one? 1/2. Cos of 30 degrees. Try it on your calculator. You have to know that without a calculator.
so
Yes, you do. Oh, I know.
To how many decimal places?
To none. You have to do it exact. Forever. Like all the decimals forever.
or the fraction.
You write it as a fraction. How do you figure out cos? Adjacent side? Square root of 3. Hypotenuse? 2. If you type the square root of 3 divided by 2 on your calculator, you'll get that same number. What is it, 0.866?
Something like that.
Yeah, okay. All right. And finally, tan of 30 degrees. Opposite, 1. Adjacent, root 3. Can we have a root 3 on the bottom? No, so we have to multiply top and bottom by root 3 and root 3, and we would get root 3 over 3. And we can do the same thing really quickly with 60 degrees. I can write this over 1 if you wanted, or you can just write it as root 3. That one triangle, well, two triangles put together, lets you figure out all of these. And you have to have it memorized for grade 11. And then we do it even bigger in grade 12. In fact, we put all of these answers on a circle in grade 12, and you have to have this whole circle memorized. All of the numbers on there. But it's not so bad. But knowing these ones really well in grade 11 will help you in grade 12. Okay, so there's two questions. You can circle 5 and 6 that are based on these special triangles. Okay, but we'll do example 1. Woo! There we go. We'll do example 1 as part of the same video. And example 1 lets you use your calculator. So, how do you know that you have to use those special triangles? Well, anything that you have to do sine, cos, or tan without a calculator on the non-calculator part is like a big hint that you're probably going to have to use those two triangles. But anything else, you can use your calculator. So we had highlighted this definition earlier. Terminal arm is where an angle ends. The angle is in standard position, so we know it has to start from the positive x-axis. And they tell us a point, so I'm going to draw a little grid. 3, 4, 1, 2, 3, 1, 2, 3, 4, there it is. 3, 4. This is the terminal arm. This is the angle in standard position. And anytime they give you this kind of information, you can make a right angle triangle and do SOHCAHTOA. And we're gonna find out that it's always best to make your right angle triangle back to your nearest x-axis. That's going to be really important coming up later, but for now, We just made a triangle. Can you see that this side is 3 then? This side is 4. Question A says, how long is it? This is the point P right here. This is your origin. How long is it from the origin to point P? Can you see that you can do a squared plus b squared equals c squared? Do some of you recognize this? This is like a very, very special triangle. It's like one of my favorite triangles. Why is it one of my favorite triangles? Because what happens if you do a squared plus b squared equals c squared? Oh my goodness. Are you okay if I don't do the plus or minus part? Probably should. Probably, like, because everybody forgets plus or minus, so I'm going to do it and take it away. C is equal to 5. It's a famous 3, 4, 5 triangle. Does anybody know other famous triangles where all the numbers are nice whole numbers? Oh, okay. Well, then I'm going to get off topic right after this question because I need to show you other cool triangles. It's like people's been holding out on you if you haven't seen cool triangles. Okay. Now, highlight again here, because knowing words is really important for being able to solve questions. Because if you watch me do questions, it makes sense. And then you get to quizzes and you're like, ooh, what do these words, what are they asking? Like, I know what to do if I know what it's asking, right? That's usually what happens. But sometimes we don't know what a question's asking, and then afterwards you're like, that's what they wanted? I know how to do that. I just, A, don't know how to read, or B, didn't listen to important instructions in class. So, the trig ratios are sine theta is a fraction. Cos theta is a fraction. It's opposite over hypotenuse, adjacent over hypotenuse. A ratio is like a fraction. So all they want is for you to label the angle theta here and write sine of theta is opposite over hypotenuse. Don't solve for theta. It says find the ratio of theta, not find theta. How are you going to remember that for a quiz or a test? That this is all that's asked for sine. All that's asked for cos is adjacent over hypotenuse. And all that's asked for the ratio of tan is opposite over adjacent. So that's part B. And then part C says actually find theta. So if I'm doing part C, I can choose, these are all really nice numbers. Sometimes there's advantage to using sine or cos or tan. They're all very nice numbers. Okay? The only thing I would say here is if you screwed up on your a squared plus b squared equals c squared, it's possible that the black number 5 could be wrong. So if I would say, is there one that's better than the others? I would probably say tan is better because I might have made a mental math mistake when I solved the 5. But we didn't make a mental math mistake. Guarantee you the 5 is right. Okay, so it wouldn't matter, and I'm going to show you on your calculator, right? How do you solve for theta? Right, we need to get rid of the tan. The opposite of tan is tan inverse. So you do tan inverse of both sides, which gets rid of the tan on the left. And if I go to my calculator, I'm in radians, so I have to hit the mode button and make sure that I'm in degrees. And if I go tan inverse of 4 divided by 3, 53.13. How much decimal places does it want me to round to? Nearest degree. Oh, 53 degrees. Check this out though, because I know that some of you didn't believe I didn't make a mistake with the 5. Some of you are still questioning my math. So I'm going to show you that if we did sine inverse, right? Sine was it 4 over 5? We get the same answer. And if you did cos inverse of the 3 over 5, you get the same answer. Your calculator has all of those angles memorized for every single try. All right. Lots of questions to circle on this one. 3, 4, 5. Well, I think I got you to circle. I got you to circle 5 already. So that's not too bad. 8, 9, 10, and 12.
I guess one cool triangles.
Yeah, other cool triangles. Definitely have to do. So we'll start off with, right, 3, 4, 5. 5, 12, 25 is 5 squared, 144 is 12 squared, 25 plus 144 makes 169. Does anyone know what number squared makes 169? 13. Beautiful numbers. I'm going to show you the third one, and I'm going to tell you that if you see a pattern that I'm doing, you can figure the fourth one out on your own. The third cool one, this is not to scale, 7, 24, and 25. And you have to tell me stuff about the fourth one. If you think you see some patterns happening. So what do you think? What do you think? Could you say one side on the next one?
The bottom one's 9.
The bottom one's 9. Oh, right. We're moving along. Good, good, good. Okay. Side 48 and 49? No, close. I like to see how you doubled, right? I like that, but did this one double? No. So pattern has to work, whatever you think.
On the sides, 40 and 41.
40 and 41. Oh my goodness. Can you figure out the next one? It's going to be?
58.
No, it's not 58.
Oh, wait, no, 20. 60.
It's 60 and 61. My goodness. Right?
I'm not getting it.
Did you know that? 11 squared, 121. 60 squared, 3,600. 121 plus 36 is 3721. And 61 times 61 is 3,721. Right? That's the mental math Stone did in his head. I was telling you the rest of you. So you get. What patterns did you see? And then I'm going to give you a tough one. Because I'm going to skip a bunch and just go to this one with 25. What are the other two sides? Because there's some patterns that you need the previous one to find the next one. Is that a pattern you used? What was the pattern you used to find this?
I was just like, on the bottom I would just add 2, and then like on the other sides I would just add, like I kept going up by 4. Like, so the first time you added 8
Yeah.
each side, and then you added 12, and then it was 16 and 20.
And 20. And the next one would be to add 24.
Oh.
Sure enough, that works. 13. Add 24, you get 84. And how did you find the other one?
I just did, I did one more.
One more. You notice that those ones are always one more. Wow, that's a ugly fight. We're just gonna. I know I can't handle it.
So that's never
It's too ugly a fight. Okay. That's a cool pattern. But the problem with that pattern is you need always the previous one to get the next one. I want to know if you can find a pattern how if I just gave you 9, Is there some connection between these two numbers and the 9 that you could just figure it out? That works for the other ones too. Is there some connection between the 5 and the 12 and 13?
What is it, 7?
The two numbers added together is the square of the bottom of
Yeah, 12 and 13
25.
is 25, which is 5 squared. 11 squared is 121. Now this is a little bit hard because I don't know, how many of you know 25 squared?
225.
Close, that's 15 squared.
Oh.
625. And if you cut 625 in half, you get 312.5, so that makes these 312 and 313. And if we check it out, 25 squared plus 312 squared. If I square root that, I get 313. These are called Pythagorean triplets because all the numbers are nice in a squared plus b squared equals c squared. And then, oh, now I'm feeling like I'm really getting off topic. This is connected to something famous in math called Fermat's last theorem. Have you ever heard of Fermat's last theorem?
Was the last one he made?
Supposedly the last theorem that Fermat made. So Fermat, mathematician, very, very long time ago, like 1200s, said, look at all of these nice ones with a squared plus b squared equals c squared. So mathematicians started to wonder, are there nice ones with a cubed plus b cubed equals c cubed? Are there nice ones? Are there nice ones for any number bigger than or equal to 3? And we found a book that Fermat wrote just in the sides, just like we're writing the sides of our textbook here. Historically, someone found one of Fermat's books. And on the side he said, when n is bigger than or equal to 3, there's never, ever any nice numbers that work. I have the proof of this, but unfortunately I don't have enough room on the side of my page to write it down. I'll do it somewhere else. Did we ever find the somewhere else? No. All we got was the book with the idea on the side. So then it sort of, when they found this book, other mathematicians were like, okay, well, if Fermat found it, we should be able to find it. And mathematicians tried. And they couldn't. And they couldn't. In fact, it was only solved in the last, like, I don't know, 50 years. And it is now most likely assumed that Fermat had a mistake in his solution. Because every mathematician that got close prior to that, people were like, yeah, that's good, but you have a tiny mistake here. Most of it's good, but there's a little mistake. So we probably think that Fermat also had that little mistake because it took like a bunch of supercomputers and 200 pages of different possibilities. Like, this is hard. Like, how do you know, it's one thing to show it never works for any numbers to infinity. But then you also have to check all numbers n to infinity. Like, who's to say that maybe when the exponent is 1,153,802, it works? Maybe that's the first time it works. It'd be hard to prove all of that, right? So that's where this, like, supercomputers and checking bunch of things had to do thousands and thousands of calculations to show that something doesn't work. It's usually quite hard in mathematics. But this has now been proven.
Oh, so he was right.
He was right, but he probably didn't have the correct proof, because the correct proof was only figured out 800 years later, or so. So it's kind of a cool story.
It's just that.
So, yeah, he was a supercomputer at that time. Okay. That video has a lot